Hello everyone, my name is MD Shahadat Hossain. I am doing thesis under Dr. Malik Mohboob. Today I will be talking about solving constant partial CPNet. Today I will be discussing about CPNet and induced graph, generation of constant partial CPNet instances for testing the algorithm. I will talk about the algorithm itself, which is search partial CPNet, and also I will talk about result and evaluation and future work. To understand CPNet, we need to first understand user preference. So user preference can be two types. One is qualitative and another one is quantitative. So in quantitative preference, user basically describe about their preference based on the quantity of a particular product. And in qualitative preference, user discuss about the quality of the product, like it can be a car, it can be choice of any grocery item or anything like that. And transitivity means like if user prefer a item, let's say item B, user prefer item B than A, and there is another item C which user prefer than B, that means C is the most preferred item, so it will be preferred than A as well. So this transitivity holds for user preference. If user gives preference between two items and we can make the relation of transitivity, we will do that. An example of a CPNet can be like that, where this is basically a preference order. Like let's say user have multiple option of choosing car, where car one is have the following properties: red as color, type SUV, then the price is low, and um, it is all-wheel drive. It is not all-wheel drive. So car 2 has the following attributes and so on. So from this choice of the car, we need to suggest which is best for the user. So in conditional user preference, user will give some conditions based on the attributes. Let's say if the color is red, I want SUV, not a compact car or a minivan. Or if the price is low, then I will go for SUV. If the price is high, I will not go for SUV. I will go for compact or minivan, something like that. So these are the conditional preference. And when we represent this conditional preference using a graph, we call it um, a CPNet, conditional preference network. So, so here we can see an example of a CP network. So here, let's say user preference is described such a way: if uh, the car is a all-wheel drive, then and the price is low, then user will prefer SUV than minivan. So this is the preference order, like SUV is preferred than minivan. There can be like more um, items as well, like here we are talking about two, which is like SUV and minivan for type, so there can be multiple types as well. And from this graph where it shows the user preference, let's say this one says that if it is all-wheel drive, the price is high, then still user prefer SUV. But if it is not an all-wheel drive and the price is low, user will go for minivan. So in that time, user prefer minivan than SUV. So we need to, the goal of my research is to generate an algorithm which will give the user the best option from all the possible items that is available. So from this CPNet, we can draw the induced graph, which is described in here, where in each label there is only change of one value. Let's say this one, where it says that it is all-wheel drive and the price is low and the item is an SUV. This is the sorry. So this is the best option that the user can get. So if we can give the user a car which is all-wheel drive and the price is low and that is SUV, then this will be the best choice for the user. And if it is not an all-wheel drive and the price is high and that is a minivan, it is the worst choice for the user. So in this graph, what we show that from this level to the next level, there is only one value that is changed. Let's say from here to here, only the change is in um, the all-wheel drive type. So if AWD is yes, then uh, user between these two type, user will prefer this one than this one. So here we are basically talking about basically the ceteris paribus, uh, where all attributes are same. Only if we change one attribute, then which one user prefer. Let's say we have two car which is like all-wheel drive is no, the price is high, and that is minivan. And there is another car where everything is same, only the change is in all-wheel drive type. So that one is like whether it is all-wheel drive, the answer is yes. So in that time, what is the user's preference? So based on that, we can draw this induced graph. So in this induced graph, each level is being preferred than the next one. So this way we can draw the induced graph from a CPNet. So if we place a car in each of these items, we can say that which car should be preferred by the user or something like that. Okay, after that, so this is another example of a CPNet. So if you see closely, then you will see that in this example, we don't have the total order. So here the total order means if we have like for a particular attribute, there is like let's say three values and we cannot order between that three values. So in that time we call that partial order. So when we have a partial order, we call the CPNet as partial CPNet. So in this example, user prefer A1 then A2, A3 then A2, then A2 then A4. So this is a you can say a partial order because we prefer A1 then A2, then A3 is preferred than A2, but there is no preference relation between A3 and A4. So we don't know that if there is A3 and A4, which one we will prefer. So in this case, there is a possibility that a solution with A3 will also be a optimal solution, and also a solution with um, sorry, not A3, you can say A1. So here you can say that A1 and A3 both is preferred than A2. So if we get two, let's say two item where the attribute is A1 and A3 both are present, we will not be able to sort between that two. So that two can be the preferred item for the user. And here only this one, like for A2, this is a total order, and A3B1, this one is a total order. Rest of those are actually partial order. So this is called a partial CPNet, while where the this is also a conditional preference network, because as you can see that the value of B, this one depends on A, and the value of C depends on both A and B. So the value of C is conditionally dependent on A and B. So this is a partial CPNet, and the algorithm basically works on this partial CPNet. So to test the algorithm, first target was to generate the data. So we have not used any real world example, or we could not collect data from real world because my goal is to test the algorithm itself, not to generate data from the database or something like that. So for testing the algorithm itself, I have to create a generator that can generate as much data as we need for testing the algorithm. Let's say the generator that we have designed can generate CPNet with 25 variables. So with 25 variables that can have domain, the domain size is basically determined by mm, based on the variable itself, and there is another constant value. Based on that, the domain size is determined using RB model. And to generate the CP, after in the CPNet we have following items like variables, domain. So each variable domain means the values of each variable. So let's say variable A can have domain 5, which means A1, A2, A3, A4, A5. So these are the values for variable A. And tuples means the preference order. So each tuple will have two values, like 1 is preferred than 3 or 2 is preferred than 5. So each tuple will determine the preference order between any two values. There will be dependency. Dependency means the as we are drawing a CPNet, which is conditional preference. So condition is basically dependency here. So if we say that B is dependent on A, which means B is conditionally dependent on A. Based on A, user will choose B. And hard constraints. So basically, our algorithm will be working on not only partial CPNet, it is constraint partial CPNet, which means in this conditional preference network, which is a partial, we will have some constraints, which is hard constraints, means that there will be, like, let's say any two attribute, let's say attribute A and B, there is a hard constraint that if A1 is chosen from A, then user will hardly choose B1 from B. So this kind of hard constraint will be there, which will also have like impact on the overall CPNet. So we need to consider those hard constraints as well. For the generation of partial CPNet, we have used RB model. So basically the input for this RB model will be a variable, a number of variable n, the tightness p, and there will be two constant alpha and r. Based on these variables, based on these values, we generate the whole CP network. So how we determine the domain size? The domain size is determined by n to the power alpha. The number of constraints determined by the equation Rn ln n. So here R is a constant value, and number of incompatible tuples determined by PD square. So where P is the tightness and D is the domain size. And the phase transition, this phase transition indicates where the transition occurs. So that means that after a certain point, there will be no solution for the partial CPNet. So that phase transition occurs in a particular value, and that one is determined by this equation 1 minus e to the power minus alpha by r. So based on this input, we will generate our CP network. So this is a example of the generated CP network. So let's say our CP network looks like this graphically, which we will be determined by the value at the left. So where it says that AA means for value variable A1 is preferred than A2, A3 is preferred than A2, and A2 is preferred than A4. So this is how the values generated. And this, let's say this is an example of this graph, but for testing purpose, what we have generated, like we have done the same thing for 25 variables with um, um, like at most 25 variables. It can be user's choice. Based on that RB model, user can set how many variable will be there, what will be the value of alpha, what will be the value of R, and so on. And using those input, our CP network will be generated. So also the generator will generate hard constants as well. So the number of hard constants are also determined by the RB model as well. So in hard constant, there will be like two variable, and there will be two value from each variable. Let's say A and B. So for A and B, we preferred A1, then B1, something like that. Sorry, if we choose A1, we will choose B1. So hard constants works like that. And hard constants also does not depends on the dependency. Let's say B depends on A and C depends on A. C depends on both A and B. That doesn't mean that the hard constant of C will always contain A. Let's say there is another variable D. There can be hard constant, like if we choose C1 from C, we will choose D1 from D. So there don't need to be any conditional dependency between two variables to have hard constant between those two. Generation of conditional preference. So here there are like four criteria that we had to consider while we generated the CPNet, as we are generating the CPNet based on uh, RB model, and the whole network is random. So we have to consider like these four things. There is like all possible combination of dependent variable. If C is dependent on A and B, we need to make sure that for all value of A and B, and the combination of A and B for all kind of combination, there is a preference order for C. So the order can be partial, but there should be a preference order. There should be no cycle. Let's say we cannot say A1 is preferred than B, B1 is preferred than B2. Sorry, A1 is preferred than A2, A2 is preferred than A3. That we cannot say that A3 is preferred than A1. In If we say that, then there will be cycle. We have to make sure that there is no cycle in the preference order, and the order should be partial. So to make sure that the order is partial, we have introduced another variable, which is P. So user can choose like on how much partialness will be there. If we say that 60% partialness, so there will be not a total order, but 60% will be in order and 40% will not have any order. So we can tune that one using another variable as well. And there should be transitivity. So if the generator generates that A1 is preferred than A2, and then A3 is preferred than A2, so the generator will automatically say that A1 is also preferred than A3. So this transitivity relationship also considered when we generate the CPNet. So after we have done with the generator, we have used those data to test our algorithm. The name of our algorithm is search partial CPNet. So this is basically so in this algorithm, what we have done is, so in this algorithm, these are the inputs. So we will be giving an input of acyclic partial CP network, the hard constant, and the assignment. So this is basically a recursive algorithm. The output will be Pareto optimal solution. And so basically the basic algorithm is designed to provide us the optimal solutions, but there is a possibility that some solution is dominated by another solution. Like we can achieve one solution from another solution. So even if two solution is optimal, that doesn't mean that those solution will not be no dominated by other. So we need to generate the set of solution which is Pareto optimal. And we have domain variable ordering. So that one is also there in this algorithm. We have done pruning in this algorithm, and this one works on a partial CPNet. and in each phase it will generate subpartial CP net, and based on those subpartial CP net the recursive algorithm works. So we have done two kind of testing to get the Pareto optimum solution. One is domains testing and another one is ordering query. And this is the snapshot of the algorithm. We have implemented this algorithm in Java to test with the generated data. And this algorithm basically gives a tree. So this tree indicates how a Pareto optimal solution can be achieved. So as you can see, there is a possible solution A1, B1, C1, and there are some cross over there and T. So that cross means this solution is not possible because there is a hard constraint. So hard constraint says that if we choose B equal to B1, let's say. So if we choose B equal to B1, we will choose C equal to C1. So we cannot choose C2. And this one, let's say T means it is pruned because we got another solution which is preferred. So this branch is pruned because we will go with the branch while there is less constraints. So something like that. And we have evaluated the result of CPNet where the variable size was 10, 15, and 20. And we have run random instances and test the algorithm whether which one gives us the result faster. So basically the evaluation criteria between two algorithm between this, so there is like two particular testing that we have done. So for the same algorithm, to choose between two solution, we have like dominance testing and ordering query. So what happens is domains testing. In domains testing, it is gives us total result, which is takes much time. And for ordering query, it gives us the result very fast. But there is a possibility that two solution is not um, totally Pareto optima, which means there is a chance that one solution is dominated by another solution, but where ordering query gives us both of the solution. So we need to judge between these two algorithms whether we want fast solution or we want the solution which is have the less number of solutions. And we calculated the running time between these two test results. And we also have checked the correctness, whether the solution that we are getting is the correct or not. And there is a chance like if we give some more constraints, there is a possibility that there is no feasible outcome as well. So we have considered those in our result and evaluation as well. So this is the sample table where we put the data of our test result. So this is, let's say the partialness is 40%, and we have taken the variable like 10, 15, 20, 25, and we see how much outcomes are there and how much time it is taken. So for ordering query and for dominance testing, we compared between the time that it takes. And in future work, we have a plan to work on like our consistency, forward check, and maintaining our consistency. So we will introduce this in our algorithm so to check whether it can increase the efficiency of algorithm in terms of runtime, because what we have seen, if we see the result, we can see that it takes around 1906 second to generate data with around 15 variable. So we are still working with 20 and 25 variables to check how much time it takes, and our target is to lower the time that it takes. So our target will be to use our consistency or forward checking to to decrease the runtime, and study the effect of variable ordering on the partial CP net. So currently we have not done any variable ordering in the CPNet, so we will try to do that and try to improve the efficiency of the algorithm. And after the final after these are done, we will design an efficient methodology to solve constant partial CPNet in practice. So after evaluating our consistency, forward checking, maintaining our consistency, we will propose a solution which will be which we can use in our um, day-to-day life for solving different problems. So this is the target for the final outcome for my thesis. So these are the reference. Comment in the section if you have any question. That's all for me today. Thank you.